Understanding path loss, and hence whether a radio ham can communicate, is easy. Let me explain. Here's a typical 2-hop path from Russia to the United States, around 8,000 kilometers over the ground. That's about the maximum range for 2 hops. The beauty of working in decibels is that we can add up all the different parts of the path loss equation. So we can hide the maths in standalone terms describing each bit of the path. Simply, there are terms for this and terms for that, and they all add. Here's the basic loss equation with the answer in decibels. There's the free space loss bit. There's a frequency term 20 log f, where f is in megahertz. So for 14 megahertz, that gives us about 23 decibels. That loss is there regardless of the path length. It's there effectively as soon as the signal leaves the transmitting antenna. Then there's a distance term. If the path was short and in a straight line through the troposphere, the loss would be 20 log d, the distance between the stations. But in the 2-hop case, it's p prime, the total length traveled, up into the F2 region, down, back up, and down again to the receiver. In this example, let's say it's 9,000 kilometers, a loss of 79 decibels. Then there's a constant 32.45. This applies when there are isotropic radiators at each end. Antennas themselves are dealt with separately. Like other parameters like transmitter power, antennas are out with the path loss calculation. Adding that lot together gives a path loss of about 135.45 dBi. So, if we transmit 1 watt, then free space loss applies, we'll receive minus 135.45 dBW, well above the receiver threshold of around minus 149 dBW, and reading something like a signal strength 4 on the meter. But there are extra losses, and it's those that make skywave propagation very different from that through the troposphere. Firstly, the wave enters and leaves the ionosphere a couple of times and experiences resulting absorption. The absorption term, Li, is determined by some complex maths involving the smooth sunspot number and parameters describing the model built from ionoson data over many years. This term has a huge influence on whether the received signal will be above the receiver threshold or below. Then there are 4 other terms, Lm, Lg, Lh and Lz. Lg, the ground reflection term, is typically low. Depending on choices the radio amateur makes, Lm and Lh could each be 0. That leaves Lz covering other losses of up to about 10 decibels. In the end, adding all these losses and using the final path loss, Lb, will tell us whether a path will work and with what reliability. Remember of course that the path loss is the median, and if we're prepared to accept a lower chance of success, more path loss can be accepted. Also remember that even if the dBs add up to something that will work, the local noise at the receiver may degrade the threshold to something unworkable. Local electrical noise is significant at HF. Making a prediction is a matter of using a computer tool. Any HF Skywave prediction tool must embrace the decibels defined in each of the terms described here, then inserted between the transmitter effective radiated power and the real receiver threshold in a path budget.